All right, should be Friday for us when we're doing this problem. This is a little 7-minute, 5 and 6. Should be doing on Friday, and I'll probably post the answers on Friday so you can see them. This is number 6 on the 2016 exam. This is a little 7-minute 4-pointer at the towards the end of the exam. This, I think, is especially part B here, is a tough little question. They give us some weird compounds to start. They give us this K value that we start not exactly sure why that's sitting there. And so not a terribly, especially A is not terribly difficult. B takes a huge understanding of chemistry, and it's really about seeing the verbiage, knowing that we're doing something, and then equilibrium is being reestablished, which means we're not at equilibrium, but we have starting values, which means we got to solve for a Q here in B, which is a little weird. It catches us off guard. So here we go. It says we got some kind of barium mixing with this EDTA thing. It forms complex whatever, and so we have these two that are forming this barium EDTA, and it gives us volumes and concentrations of both of the reactants. And then it says, considering the value of K, determine the concentration of this thing in the 100 mils of solution. And so we can get caught trying to set up an equilibrium expression. When it says consider the value of K, look at K. It is huge. 7.7 times 10 to the 7th power means what happens to this reaction? Which direction does it favor? It favors the products heavily, so heavily that at that big a K, we would just say this reaction is going to go to completion and form all products. So on the first one, if you can understand that it's going to completion, it's not that hard of a problem. We've got barium ions reacting with this EDTA to produce this compound. And they give us 50 mils of the EDTA at the beginning with a concentration of 0.3 molar. And so when we get it like that, we can solve for moles, turn volumes and molarities into moles. That gives us 0.01 moles of EDTA. The barium, we've got 50 mils of it at 0.2 molar, and so that gives us, when we multiply those together, 0.01 moles of barium. Does it hurt to show that work? It doesn't hurt to show that work, so if you want to show that work there, stop bobbing. If you want to show that work there, I think it's really healthy to put down 0.3 molar times 0.05 liters, and 0.2 molar times 0.05 liters. That's where we're coming up with those mole values. Good. It wants to know on A, what is the concentration in 100 mils of solution? So when those moles react, one of those is going to be our limiting reactant. Which one? Because they're a 1-to-1 ratio, the limiting reactant there is going to be our barium. And so when those two react, how much of this is reacting? All of it. And that then, because it's the limiting reactant, is going to determine the amount of moles of product. This thing goes to completion, which means this is going to react and move to the product side until all this is gone. So we got 0.01 moles of the barium product. And so the concentration of that at the end is going to be, and I would probably do it this way, write it out so they can see it. The concentration of that thing is going to be 0.01 moles divided by the cumulative volume, which is 0.1 liters, and so the molarity is 0.1 molar. Because they say something about K at the beginning, considering the value of K, I would put 0.1 molar, because large K means reaction goes to to completion. The answer there is that 0.1 molar barium. We should carry another sig fig or two. If you put 0.100, probably even better. Good, that's part A. Part B, they say, solution is diluted with distilled water to a total volume of 1 liter. After equilibrium has been reestablished, so we're no longer at equilibrium. After equilibrium has been reestablished, the number of moles of barium greater than, less than, or equal to the number of barium present in the original solution before it was diluted. What we've done here is change the concentrations of the reactants and the products that are still present. And so we've got to look at the Q value here, and we're going to do a little shorthanded Q value. Our Q value, products over reactants, means we're taking this barium mess we got at the top over the concentrations of barium in that complex ion, like this. What did we do when we added changed the volume by tenfold? We added 900 mils of water to this to give us a total volume of 1,000, which means we took the concentration of this and made it a tenth of what it was. So our Q value here would be a tenth of the original concentration of the top one. The bottom one's also got lowered down to a tenth of their original concentration, which means what happened to the Q value here? That's 0.1 divided by 0.01, and so that gives us 10 compared to the original, well, it would have been just 1. Changing everything by a tenth of those concentrations it makes the Q value 10 times bigger than the K value. The K's not 1, the Q's not 1, it's a little shortcut for us. We just need to know that it's 10 times greater. And so when we set these things up, K and Q is greater than K, that means that this reaction is going to shift towards reactants when we change those concentrations. And so when we change those concentrations, this guy now has to shift towards the reactants. And so what's the question? The question is, and this is all justification, by the way, what we've just written there, but after equilibrium reestablishes the number of moles of barium present in the solution greater than, less than, or equal to the number of bariums present in the original solution. Barium ion concentration. That's probably the wrong way to do it. Barium ions will be greater because the dilution causes equilibrium to shift toward reactants. It's not really a math problem, it's a conceptual problem. That's a tough little conceptual problem there. The point breakdown there is 1 for knowing barium ions will increase or will be greater, and then 1 for the justification. This is the justification part, the part that Q is greater than the original K, causing that shift towards reactants. Tough little problem there. Number 6.